Hello everyone, and welcome to the second and final part of this talk on symmetries and instantons on special harmonic manifolds. Now, before moving on with the talk, let me quickly recap what we saw in the first part of this talk. So first of all, we considered S1 invariant hyperkähler form manifolds, and we showed that all S1 invariant abelian instantons in this case are determined by the choice of a harmonic function on R3. And this essentially followed from the Bogomolny equation. Then we move on to S1 invariant G2 manifolds, and we derive an analog of the Bogomolny equation in this context, and we deduce from this that Killing vector fields gave rise to abelian G2 instantons. And we saw how this can be applied to cohomogeneity G2 manifolds. In particular, we looked at the spinor bundle of S3. After that, we discussed the apostrophe of Salmon construction, which essentially was imposing that the S1 quotient of a G2 manifold is a Kähler manifold. And this gave rise to a Hamiltonian Killing vector field, which by taking the quotient of this manifold, we were able to reduce the construction of certain G2 invariant G2 metrics to a certain Kähler form manifold. And we reformulated the instanton condition on this form manifold, and we were able to produce examples of abelian instanton in these cases. So what we will do now is we will consider the sort of analogous story for spin 7 manifolds. And more or less, we will subsume the G2 case inside this context here. So we will consider S1 invariant and T2 invariant spin 7 metrics, and we will derive a Bogomolny and Hitching type equation in this context. And we will also describe an analog of the apostrophe Salmon construction, which will help us produce very explicit examples of T3 invariant spin 7 metric. So essentially, we will show that there exists a spin 7 lift of the apostrophe Salmon construction. And we will construct explicit examples of abelian instanton in this case. And finally, I will finish off by mentioning certain examples of calibrated submanifolds in the G2 and spin 7 example that we discussed in this talk. Since after all, this talk is part of a series in calibrated geometry and gauge theory. Okay, so let me get started. So to begin with, let me quickly remind you what is a spin 7 manifold. So a spin 7 structure on an 8 manifold is determined by an algebraically special 4 form, capital Phi here, which at every single point is given by the following expression. So this is a model on R8, where Phi node here is a standard model on R7 that we seen in the first talk, and we are extending R7 to R8 by the addition of this coordinate X node here. And just like in the G2 case, this data will determine spin 7 manifold if the holonomic group is contained in spin 7. And this happens if and only if the 4 form is covariantly constant with respect to the Lev-Shifter connection, or equivalently, as shown by Marisa Fernandez, that the 4 form is closed. Now, we are interested in instanton on spin 7 instanton. So in this case, a connection form A is said to be a spin 7 instanton if its curvature form belongs to the holonomic algebra, so spin 7. And this happens if and only if the curvature form, when you wedge it with the 4 form and you hot star it, you get minus of the curvature form. So this is the analog of somehow the anti-self-Joule condition we saw on a 4 manifold, and also in the G2 case. Now, we're interested in S1 invariant spin 7 structure. So as before, we will consider an S1 action generated by a Killing vector field X as before, which preserves a 4 form. And just like in the G2 case and the hyperkähler case, we can define a canonical Riemannian connection, theta, by this expression here. And V here will, as usual, denote the inverse norm square of this Killing vector field. Now, the quotient space is going to be a 7 manifold now, and it will inherit a G2 structure determined by the freeform V here. So this freeform is defined essentially by contracting the vector field with the 4 form here. So you can see from this model, for instance, that this will define a G2 structure. Now, this G2 structure in general is not going to be torsion-free. Instead, but it is always going to be closed. So the freeform is always closed, but it's not co-closed. And instead, the exterior derivative of the 4 form is given by the following expression here. So I need to tell you what do I mean by d theta 214 here is the projection of d theta into the G2 algebra. So remember, the space of 2 forms on our 7 manifold will split into a G2 component corresponding to the inclusion of G2 into S07, and then an orthogonal complement to that, which is essentially as a G2 module isomorphic to R7. So this term here essentially is a production of d theta inside the G2 component. Okay, so now we're interested in spin 7 instanton. So what is a instanton equation in this case? So suppose we're given a connection form A, which is S1 invariant. Psi, as before, is a Higgs field, and B here is going to be an S1 invariant connection form, which will descend down to the quotient, so the 7 manifold. Then the spin 7 instanton condition can be reformulated into this Bogomolny type equation, which is very sort of similar to what we saw in the G2 case. In particular, you see that if you apply Hodge-dot on both sides of this equation and you take the exterior covariant derivative with respect to the connection, you see that the Laplacian of this rescaled Higgs field is again, as in the G2 case, given by some pairing of the curvature form of the connection form B and that of the S1 bundle for the quotient from the 8 manifold to 7 manifold here. So here d theta to 7 is a projection of d theta into the R7 component that I just mentioned earlier. So as in the G2 case, again, the simplest setup is when the connection form vanishes on the quotient space, so B is 0. And we see that we can solve this equation here, if this term here dies, simply by setting psi here to be V to the minus 1. And we deduce, as in the G2 case, that if a vector field preserves the full form, then the exterior covariant derivative, the exterior derivative, sorry, of the dual one form to this scaling vector field belongs to the holonomic algebra, spin 7. And when V is equal to 1, so when this S1 fibers have constant size, then the space, our spin 7 manifold, splits as a Riemannian product. So it's a G2 manifold cross an S1. And this equation here reduces to what is known as a G2 monopole equation. And if we set psi here in actual to be 0, then this term here vanishes, and we get that this term here has to vanish as well, which is precisely the G2 instanton condition. And just like in the G2 case, where we look at cohomogeneity 1 examples of G2 manifold, we can look at cohomogeneity 1 examples of spin 7 metrics. So one of the first examples is the spinor bundle of S4, which admits a Brand-Simon metric, and this manifold has sp2 times sp1 as group preserving this 4 form. So the sp2 is coming from the S4, and this sp1 here is coming from the fiber direction, which is R4. And because this group here has dimension 13, immediately we deduce that there's at least going to be 13 abelian instanton in this case. There are also other examples of cohomogeneity 1 spin 7 manifolds, which have group preserving the isometric group U3. So these are spin 7 manifolds which have the allocollic space as a principal orbit. So this was shown to exist in the work of Svetic, Gibbons, Liu, and Poe back in 2002 by numerical analysis, and this was rigorously shown to indeed define complete metrics in the work of Bazaike. Okay, so let me now consider an enhanced symmetry. So when instead of just having an S1 action, now we have a T2 acting on our spin 7 manifold, which preserves again the 4 form. And I'll assume for simplicity that these two vector fields generating this torus action are in fact orthogonal. Then, as in the previous case, we can define a connection for theta and the function v here as before, but now we have 2 of them corresponding to each of the killing vector field. Now the quotient space, which is now going to be a 6 manifold, inherits an sq3 structure. And here's the data determining this sq3 structure. As before, G omega here is a metric, J is an almost complex structure, little omega here is a non-degenerate 1-1 form, and this is a complex 3-0 form. And this expression here tells you how these data here, together with the connection form and this function v, determine the spin 7 structure. And the natural question to us is, well, what is the intrinsic torsion of this sq3 structure? As in the G2 case, it's not going to be torsion-free, but it is always going to be symplectic, so the 2 form is always closed. But the almost complex structure doesn't vanish. In general, it will vanish if and only if the 1-1 component of these two connections formed, θ1 and θ2, vanishes. So in the G2 case, there was only one connection formed, and we saw that indeed it was a 1-1 component determining the Nin-Heist tensor. Simple remark is that this manifold here, the quotient space, is going to be a Calabi-Yau free-fall if only if both of these functions here are constant. In other words, the S1 or the S1 fibers, both of them, need to have a constant size. So this almost complex structure, I should have mentioned earlier, was actually studied in certain cases. For instance, in the work of Acharya, Bryant, and Salmon back in 2019, they studied the S1 quotient of the anti-self dual bundle of S4, which admits a Bryant-Salmon metric. Well, they studied the cone metric in this case and described explicitly its S1 quotient. And they worked out very explicitly the almost complex structure J in this case and studied its Nin-Heist tensor. And previous work of mine, I studied the T2 quotient of the spinor bundle of S4. And again, the almost complex structure it's generally almost complex. It doesn't vanish in general. The Nin-Heist tensor doesn't vanish in general. Okay, so in this context, I need to tell you we're interested in instanton. So what is the T2 invariant instanton condition? So here it is. Suppose we have a connection form A, which is invariant, and psi1 here and psi2 are both Higgs-field on the 6 manifold, and B here is a connection form, and everything here is T2 invariant. Then the connection form A is going to be a spin 7 instanton if and only if this following condition here holds. So this is some sort of a Hitchin type equation, the Hitchin type equation for this T2 reduction of the spin 7 instanton condition here. And again, as before, dB here denotes the exterior covariant derivative on the 6 manifold, and the subscript, the superscript C here denotes the fact that I'm composing with the almost complex structure J as well. And here this is simply the Lie bracket depending on the gauge group G that we're working with. So simple observation is that if you set psi1 here to be 0 and one of the S1 fibers to be constant, then this is precisely asking that our manifold is an S1 cross a G2 manifold, and we recover indeed the G2 instanton condition. Okay, the S1 invariant G2 instanton condition that we investigated in the first talk. So as in the Apostol-Salmon case, we will now consider the case when this almost complex structure is in fact vanishes. So our 6 manifold is indeed a Kähler manifold. Then one can again define a Hamiltonian vector field on this 6 manifold, and again we can consider the Kähler reduction of the space. In other words, we can reformulate the spin 7 PDs in terms of this data on this 4 manifold. In fact, in this case is actually an extra piece of data that it's not going to be important in this talk, but it's worth mentioning that in fact there's a dichotomy in this case because we have 2 functions, V1 and V2, so we can use each of them as a Hamiltonian function to produce in principle 2 Hamiltonian vector fields. So, but if they are dependent on each other, then we get only 1 Hamiltonian vector field, in which case we can only do 1 Kähler reduction. But if they were independent, then in principle you could reduce all the way down to a 2 manifold, so just a Riemann surface, and then you can again invert this construction to produce spin 7 metric. But this is not what I will cover here. Instead, I will just look at the case where we have this reduction to a 4 manifold. So this is an analog of the Apostol-Salmon construction for spin 7 metric. So we get a very sort of similar theorem as in the G2 case. So we get, if we have a 1-parameter family of Kähler forms on our 4 manifold with a family of positive function satisfying the following pair of conditions, then we can define a spin 7 metric on a T3 bundle. So this is locally isomorphic to a T3 bundle over this 4 manifold, where the T3 bundle is determined by its curvature form, and this is the data determining this T3 bundle, and you cross that with R+. And you can check that this 4 form here and this metric here will determine a torsion-free spin 7 metric. Okay, so this is essentially a lift of the Apostol-Salmon construction. So I should say that in this case, it's not the case that the metric will have holonomy contained in strictly contain spin 7. Generally speaking, the holonomy will actually be equal to spin 7. And here is the simplest sort of example, just like in the Apples of Salmon case. I'll consider the case when we just have a hyperkähler form manifold, which is just R4, in which case you can work out that the connection forms can be explicitly given in this coordinate system here, x1 up to x4 denoting the coordinates in R4, and 5, 6, 7 here denoting the fiber direction. And you can check that this metric here has holonomy actually equal to spin 7. You can compare this metric here with the one we saw in the first talk. And again, we can produce very explicit examples of T3 invariant instanton. So here's the first one is coming just from the symmetry, as we showed earlier that killing vector fields give rise to instanton. So this is essentially the dual of this T3 action generated by the dual of these three one forms here. But there are other examples as well, which are genuine examples of spin 7 instantons. And more or less, you can do the same sort of game for all the instantons that we saw in the Apples of Salmon case. So essentially, all these families of GT instantons that we saw before will live indeed to spin 7 instantons. Okay, so this gives a very explicit class of examples. Okay, so now let me make some remarks about calibrated submanifolds. So quick reminder, calibrated submanifolds are certain special classes of minimal submanifolds. So they're special in the sense that they are minimizers of the area functional. And by contrast to general minimal submanifolds, which are determined by second order PD condition, calibrated submanifolds are only determined by first order one. So they're often easier to find. So here are some examples of calibrated submanifolds. So for instance, if you're on a Kähler manifold, then the complex submanifolds are calibrated by powers of the Kähler form, normalized by this constant here. So calibrated means that this differential form will restrict to define the volume form on these submanifolds. In the context of G2 manifolds, we have two types of calibrated submanifolds. We have associatives, which are calibrated by the free form, and we have co-associatives, which are four manifolds, which are calibrated by the dual four form. And on spin 7, we just have one type of calibrated submanifolds, namely Kähler submanifolds, which are calibrated by the four form. And what I want to do is I want to tell you some examples of this class of objects in the examples that we've seen in this talk here. Okay, for instance, we've encountered the spinor bundle of S3, which admits the Brand-Simon metric, but also a one-parameter family of G2 metric from the work of Van Huber and collaborators. And in this case, the zero section, which is an S3, is an example of an associative submanifold, whereas the alpha fibers are examples of co-associative ones. For the anti-self-dual bundle of S4, the zero section is instead a co-associative, and the R3 fibers now are associative submanifolds. And in the case of spin 7 manifolds, for instance, we've seen the spinor bundle of S4. In this case, the zero section, which is an S4, and the R4 fibers are all examples of Kähler submanifolds. So more examples of co-associative fibration was found in work of Spiro Karagiannis and Jason Lotte in 2020, and examples of Kähler fibrations for the Brand-Simon spaces was found in work of Federico Trinca more recently. Let me mention some examples of associative fibration on the spinor bundle of S3, which, to the best of my knowledge, I haven't seen written down anywhere. So the spinor bundle of S3 admits an associative fibration by S1 cross R2, which is parameterized by S2 plus S2. So there's one slick way of saying this is to remember that the spinor bundle of S3 is topologically just S3 cross R4, which essentially you can think of as S3 cross R plus, and you join to that the zero section, which is the S3 itself. And you can, for instance, pick an S3 inside the zero section here, and you can pick an S3 in, this is a fiber, R4, you can pick an S1 here and cross that with R plus, and then this guy here will extend smoothly to the zero section to define an R2 cross S1 fiber, which is exactly the associative fibration here. And these are parameterized by a choice of a point in S2 plus S2. So other examples of associatives that that have appeared in stock are, for instance, the fibers which of the Apples of Salmon spaces, which is T2. So we have this T2 action crossed with this R direction, this gave examples of associative vibrations for the hypersound spaces, and the R plus cross T3 fibers in the spin 7 analog also define KD vibration. So for instance, this can easily be seen from the expressions that we saw earlier. For instance, the 4 form here is given by the following expression, and you will see that this term here will precisely calibrate the T3 cross R plus fiber in this instance. So there are plenty of examples of associatives and KD vibrations. These are some very simple examples of local instances of this. So thank you for listening. That's all I wanted to say in this talk, and hopefully you've learned some simple examples of G2 and spin 7 metrics, some examples of associatives, square associatives, and KD vibration, and some very concrete examples of instanton in all these cases. Thank you.